Hello students, you are welcoming the video number 13 of a chapter of chemical thermodynamics. In the video number 12, we have studied standard enthalpy of combustion and the standard enthalpy of formation. Along with that, in that video number 12, we have completed how to balance the combustion reactions. What are the rules for combustion reactions to balance them, and how to calculate the change in number of moles delta N. And now in this lecture number 13, we have to study the point of bond enthalpy. Now see here what is meant by bond enthalpy and how it is applicable in calculation of enthalpy of the reaction. Bond enthalpy is applicable in order to calculate the enthalpy of reaction. So let us see that relation. See what is meant by bond enthalpy. It is the enthalpy change required to break a particular type of covalent bond in 1 mole of gaseous molecule to convert into gaseous atoms. We know in 1 mole of gaseous molecule, how many molecules are there? Avogadro's number of molecules are there. They are 6.022 into 10 raised to 23. That much number of molecules are present in 1 mole of the molecule. All those molecules are broken and converted into the atoms. The enthalpy change required to break a particular type of covalent bond in 1 mole of gaseous molecule to convert them in the gaseous atoms or maybe gaseous radicals is known as bond enthalpy. Let us consider the example. For example, if we see the hydrogen molecule in a gaseous state, 1 mole of hydrogen is containing how many molecules of the hydrogen gas? Avogadro's number of the molecules. 6.022 into 10 raised to 23 molecules are present in 1 mole of hydrogen. All those molecules are broken and they are converted to the atoms. Hydrogen gaseous atom may be radical. Molecule is broken and converted into the atoms. So in order to break the bond, a covalent bond is broken. In between two hydrogen atoms, covalent bond is present in the molecule. That covalent bond is broken, and we know that breaking of bond is endothermic change. So here energy is absorbed, heat is absorbed, and that is known as bond enthalpy. Delta H, the energy absorbed, heat absorbed to break this bond will be equal to 436.4 kilojoule. 436.4 kilojoule of heat energy is absorbed, and that is known as bond enthalpy of the hydrogen. It is a diatomic molecule, diatomic. So it is also known as bond energy. Bond enthalpy is also known as a bond energy in the diatomic molecule. Let us consider one more example. HCl, hydrogen chloride gas. There is a covalent bond between hydrogen and chlorine. This bond is broken, converted to hydrogen and chlorine. It is the conversion to hydrogen and chlorine. So there also energy is absorbed, heat is absorbed, and that is equal to delta H is equal to 431.9 kilojoule. So this is also known as bond energy. In the diatomic molecules, bond energy is nothing but the bond enthalpy, and it is defined as the enthalpy change required to break a particular type of covalent bond in the 1 mole of gaseous substance to convert into gaseous atoms or radicals. What happens to the polyatomic molecules? In polyatomic molecule, there are many bonds present. In diatomic, only one bond is present. Here also one bond is present. But if we consider the case of polyatomic molecule like water HOH, it has two bonds, one OH and the another OH. They can also be broken, converted to EH plus OH. Here, in order to break this bond is broken, and the energy absorbed delta H will be equal to 499 kilojoule. Now the second bond is broken. This bond is broken over here. OH. Now this bond is broken, converted to H plus O. To break that bond, the energy absorbed is 428 kilojoule. For breaking of first bond, the energy required is 499 kilojoule. For breaking of second bond, energy required is 428 kilojoule. But the bond energy of this OH or even this OH in water is neither considered as 499 nor considered as 428. See how it is there. So for that purpose, the equations are added. They are broken and converted to H plus O. This is cancelled. This term is cancelled. So simply HOH will give H plus O, and delta H will be equal to 8 plus 9, that is 17. 1 is carried, 9 3 12. 1 is carried, 9. 927 calorie, sorry, 927 kilojoule of energy is required to break how many OH bonds? 2 OH bonds. It is not one OH bond. This is the energy required to break 2 OH bonds. Therefore, average is taken, and that is known as average bond enthalpy will be equal to 927 upon 2, and that comes equal to 2 4s are 8, 1 is carried, 2 6s are 12, 2 3s are 6, 463.5 kilojoule. Therefore, the bond enthalpy of OH bond is considered as 463.5. It is neither this value nor this value. What is the actual specific value of a particular bond? In order to break the first OH bond, energy required is 499. In order to break the second OH bond, energy required is 428 kilojoule. But here, the consideration of OH bond enthalpy is neither 499 nor 428. It is considered to be 463.5. And how it comes? It comes by adding these two values and divided by 2. Means what we have taken? Is it absolute value or is it average value? This is the average value. This is known as average value. Therefore, in polyatomic molecules, instead of considering absolute bond enthalpy, their average bond energy, average bond enthalpy is considered. This is the case of water, which is a polyatomic molecule. Let us consider one more molecule, methane molecule. See in methane how the bond enthalpy and average bond enthalpy are different. methane has a formula CH4. It has structure like this, CH4. The first bond is broken, it is converted to CH3 plus H. For this, delta H will be 427 kilojoule. In order to break the first CH bond, energy required is 427 kilojoule. Now the second bond, this is broken. Here it is CH3. A second bond is broken. Now it gives CH2 plus H. To break the second bond, energy required delta H will be 439 kilojoule. Now again third bond is broken. Third one, CH2. It gives CH plus H. This bond is broken. To break this bond, the energy required delta H will be 452 kilojoule. Now this bond is broken. HC, it is broken, giving H plus C, and the enthalpy change required is 347 kilojoule. We have broken 4 CH bonds. For each CH bond, the energy required to break it is different. It is different. And the bond enthalpy considered is different. So let us see how that is different, how that is calculated. What is the net reaction from this? This is cancelled, then this is cancelled, then this is cancelled. So net reaction is CH4 giving H plus H plus H plus H plus C. The net reaction will be CH4 giving H plus H plus H plus H plus C. 1, 2, 3, 4 plus C. And the net delta H will be the summation. 7 plus 2, 9, 18, 18, 7, 25. So 5, 2 is carried. 4 to 6, 6, 5, 11, 14, 2, 16. 1 is carried. 4, 8, 12, and then 16. 1665 kilojoule of energy is required to break 4 CH bonds. Therefore, what is the energy required to break 1 CH bond? For breaking 4 CH bond, the energy required is 1665 kilojoule. So for breaking 1 CH bond, energy required will be X. Doing cross multiplication, X is 1665 divided by 4 kilojoule. Therefore, X will be equal to 4 for the 16, 4 1 are 4, 2 is there, then 4 6 are 24, 1 is there, 4 2 are 8, 2 4 5 are kilojoule. 416.25 kilojoule. So the bond energy is considered as this value. Bond enthalpy considered to break CH bond is considered as this value, and this is not matching with first or second or third or fourth. It is totally different, and it is nothing but how it is obtained. Is it absolute value or is it average value? It is the average value. So average value is taken in case of bond enthalpy of polyatomic molecules. There each bond has its specific value. Each bond will have its specific particular value of bond enthalpy. But in the polyatomic molecule, instead of considering the absolute value of any specific bond, their average is taken, and that average is known as average bond enthalpy. So average bond enthalpy is the average amount of enthalpy change required to break a particular type of bond in 1 mole of gaseous substance to convert into the gaseous atoms or radicals. And from this bond enthalpy we can calculate the enthalpy of a reaction. Let us see that important point, how the enthalpy of reaction is calculated. How the enthalpy of reaction can be calculated. For example, if we have the reactants H2 plus I2 giving twice HI, this is the reaction. If we know bond enthalpy of H2, bond enthalpy of I2 and bond enthalpy of HI, we can calculate the enthalpy of a reaction. Here we are studying the calculation of enthalpy of reaction. How to calculate the enthalpy change of reaction from bond enthalpies. In the reaction, what happen we know? There is breaking of old bonds. The bond between two hydrogen atoms is broken. Bond between two iodine atoms is also broken. And there is a formation of new bond take place. Breaking of bond, breaking of old bond in the reactant take place and formation of new bond take place. Just now we have studied breaking of bond is endothermic. Breaking of bond requires energy. Therefore, formation of bond loses energy. There is evolution of energy take place during the formation of bond and energy is absorbed during the breaking of bond. So, in general we know it is the enthalpy of product minus enthalpy of reactant. We know energy of product minus energy of the reactant, that is our general statement. Final state, delta H of reaction is nothing but H2 minus H1. Final state minus initial state. But here what happened? H1 is positive. Over here these are having the positive value because they absorb the energy to break the bonds. And here this will have negative value, opposite. Therefore this become plus and this will be minus. It means that from the bond enthalpies of reactant and product, we can calculate the enthalpy of reaction by this formula. It is bond enthalpy of reactants minus bond enthalpy of products, summation of bond enthalpy of reactants minus summation of bond enthalpy of the products will give us the enthalpy of a reaction. Why this is opposite? I have explained that during the chemical reaction, old bonds are broken and new bonds are formed. Formation of bond is exothermic, therefore products will have a negative sign, and breaking of bond is endothermic, so reactants will have a positive sign. And here the answer is, the formula is opposite. Instead of product minus reactant, if we know the bond enthalpies, the formula is bond enthalpy of reactants minus bond enthalpy of the products will give us the enthalpy of reaction. Now this you will come to know very easily after demonstration, illustration with the help of one problem. So let us see that problem. Now see here, this is the numerical example. It is a numerical example based on bond enthalpy and enthalpy of reaction. The problem is the enthalpy change of the following reaction. For this reaction, enthalpy change is given. What is the reaction? CH2 plus CH4 gas plus Cl2 gas giving CH3Cl gas plus HCl gas. For this reaction, enthalpy of the reaction under standard conditions 0. This 0 indicates standard conditions, 1 bar pressure and 298 Kelvin temperature. The enthalpy of reaction is minus 104 kilojoule. Means forward reaction is exothermic. Delta H is negative, so forward reaction is exothermic. For this reaction, enthalpy of reaction is given, and we have to calculate CCl bond enthalpy. Reaction enthalpy is given, and we have to calculate the bond enthalpy. And further, the bond enthalpy of these 3 bonds is given. Bond enthalpy of CH bond is given, ClCl bond is given, HCl bond is given, and CCl bond we have to calculate. So here it is a question mark. In this reaction, what happened? While solving this problem, this reaction we can write like this also. CH4 gas plus Cl2 ClCl gas gives CH3Cl plus HCl. CH3Cl HCl gas CH3Cl plus HCl. While solving these type of problems, it is necessary to write this type of the reaction. This is the reaction given. The same reaction I can write in this format. To write this type of reaction in this format is very much important. Why? Because from this format we will easily come to know which bonds are broken and which bonds are formed. So see over here. From this reaction, what we will come to know? We will come to know that there is a breaking of 4 CH bond. There is a breaking of how many CH bonds? 1, 2, 3, 4. 4 CH bonds are broken. In order to break 1 CH bond, how much energy is absorbed? 414 kilojoule energy is absorbed. And we have to break 4 bonds. So how much energy is absorbed? 414 into 4. Then ClCl, this is reactant. Cl2 is reactant. And the bonds in reactants are broken. So this bond is also broken. In order to break this ClCl bond, the energy absorbed is 243 kilojoule per mole. And these are the products. Bonds are formed. So how many CH3 bonds are now formed? 3 CH bonds are formed. 3 CH bonds are formed. In order to form one bond, 1 CH bond, how much energy is evolved? 414. Evolved means minus sign. Absorbed means plus sign. So this much energy, 414 into 3 with a negative sign is evolved. CCl bond enthalpy, this we have to calculate. And HCl, it is formed. HCl is formed. The bonds in the reactants are broken and bonds in the products are formed. So the bond between H and Cl is formed. So whether it will have negative sign or positive sign? Negative sign, because bond enthalpy is the enthalpy change required to break a bond, but here it is the bond formation. So enthalpy is the heat evolved there, energy is evolved, this much energy is evolved, so it has a negative sign. So from this we have the equation delta H of reaction will be equal to summation of enthalpy of reactants under standard conditions, enthalpy change of reactants under standard conditions, minus summation of enthalpy change under standard conditions of products. This formula we have studied. Now just substitute the values. Delta H of reaction under standard conditions, it is given. Now reactants and products, from this we have to write. It is like this. Delta H under standard conditions of reaction will be equal to delta H naught of reactants, summation. Summation means delta H naught of reactants, CH bonds are there. And how many CH bonds? For breaking one CH bond, 414 kilojoule energy is required. How many bonds are there? 4 bonds are there. See here, 1, 2, 3, 4 bonds are there. Therefore, this is multiplied by 4. Energy is absorbed. Plus another reactant. Which is another reactant? Over here, ClCl. It has energy 243. Means it is delta H naught of ClCl. How many? Only one. Only one delta H naught of ClCl. These are having the positive sign. Now minus products. Delta H naught of the products. How many products? 3CH, 1 CCl and 1 HCl, minus products I am writing over here. First one, 3 delta H naught of CH. Why this multiply? This is multiplied by 3 because 3 bonds are formed. So it has a minus sign. For that minus sign I am writing here so that you will easily come to know. Minus. Then minus. How many CCl bonds are formed? 1 multiplied by delta H naught of CCl. Minus HCl. How many HCl? Only 1. So 1 multiplied by delta H naught of HCl. Now substitute the values, or we can cancel the similar terms also. Delta H naught CH 4 minus 3, it is just 1. Delta H naught of reaction is given. Delta H naught of reaction is minus 104. So here it is minus 104 is equal to 4 delta H naught CH minus 3. It is nothing but 1 into delta H naught of CH plus delta, it is also 1 delta H naught of ClCl minus, this we have cancelled because 4 minus 3 is 1. So it is cancelled. This I have written minus, so now this is this one into delta H naught of CCl. This is what we have to calculate. Minus 1 into delta H naught of HCl. Now substitute the values. We know all the values. Substitute them. Minus 104 is equal to 1 into delta H naught of CH given 414 plus delta H naught of ClCl. Delta H naught ClCl is 243. 1 into 243 minus 1 into delta H naught of CCl. This we have to calculate. 1 into delta H naught CCl we have to calculate minus 1 into delta H naught of HCl. HCl, that is the value of HCl 431. Now we can simply calculate the answer. Minus 104 will equal to 414 plus 243. Then this is minus 431 minus delta H naught of CCl. Just solve it. Minus 104. Then 4, 3, 7, 1, 4, 5, 4, 2, 6, minus 4, 3, 1 is equal to minus delta H naught of CCl. Solve this now. Minus 104 is equal to 7 minus 1, 6 plus sign. 7 minus 1, 6. Then 5 minus 3, this 2. 6 minus 4, this is also 226. Now this is taken on left side. Minus delta H naught of CCl. Now if we take delta H naught CCl on left side, it will be plus. This I am taking on left side. So delta H naught of CCl, it becomes plus on left side. This I am taking on right side. So it is 226. This is minus. On right side it becomes plus 104. Therefore delta H naught of CCl will be equal to 330 kilojoule per mole. To break 1 mole of CCl bonds, the energy required is 330 kilojoule. In that manner, we have calculated this value. We know the reaction enthalpy value. Enthalpy of reaction is given. Bond enthalpies of 3 bonds are given. And they have asked to calculate the bond enthalpy of 1 bond. And by this format, we can calculate it. See, otherwise, what they are doing? They are giving this value. If this is given and this is asked to calculate, that is also very simple. This value is given as 330. If we know here 330, we can calculate this because this is the formula. This value we have to calculate at that time, and this value is given. CCl is given 330. So substituting this value here 330, every time we can substitute 330 and we can calculate the left side delta H naught of the reaction. Thus it means that if we know the enthalpy of reaction under standard conditions, we can calculate the bond enthalpy of any bond under standard conditions, or if we know the bond enthalpy of all bonds in a reaction, we can calculate the enthalpy of reaction. There are many problems given here. We have supplied you workbook. In that workbook also I have included certain problems. So take the print of that workbook and you have to solve all those problems. In the next lecture, next video, we will see the Hess law of constant heat summation.